The last major topic of acid-base equilibrium is understanding buffers. So buffers are special solutions that can resist a change in pH. So these are very important chemically, but maybe more important biologically. So what a buffer is able to do is to neutralize added, or sometimes we use the phrase invading acid or base. That keeps the pH of whatever that buffer's in about the same. It doesn't mean that it keeps the pH neutral or 7. Some buffers can do that, but other buffers will just hold the pH wherever it needs to be. So you'll find buffers that exist in a lot of foods. And if it's maybe a sour food, that would be keeping the pH lower, around 2 or 3. So that happens in some sodas. A lot of pHs, solutions that we use on or around our body, maybe contact lens solution or different things that we drink, soaps, shampoos, facial cleansers, etc., have a certain pH that they're supposed to maintain to be safe for their use. Sometimes a lower pH, very often around 7 to match our body's pH, a little bit above 7, or for cleaners and cleansers, an even higher pH. But what the buffer does is it can react in order to keep the pH very close to the same. The way it can do that is by being able to neutralize more acid and being able to neutralize some base. The way you can make a solution that does that is make a solution that has a significant amount of an acid and a base. And it's most commonly a weak acid, or it needs to be, a weak acid with its conjugate base, or a weak base with its conjugate acid. And we'll see examples of each. So the buffer itself is the solution that has both acetic acid and the acetate ion. And notice that it doesn't just say acetate, because we can't go into the lab stockroom and find acetate. That acetate, or that anion of the conjugate base, needs to be paired with something that's neutral. So sodium or potassium or calcium, a cation from a strong base that doesn't have any acidic or basic properties itself. When you have both of them there, you have both an acid and a base. So we're going to look at that and how it would act. So this is maybe the reaction, or what happens when we make the acetate buffer. So when I take acetic acid floating around in the solution, I'd have a significant amount of acetic acid. That's weak and ionizes very little. So if I didn't put anything else in there, I'd have a whole bunch of acid molecules, a small amount of hydrogen, and a small amount of acetate. That would be able to react with the base, but there wouldn't be enough of the acetate to react if I put more different acid in there. So then I would need to add something that can provide the base, the conjugate base, sodium acetate. The sodium's going to float around as a spectator, but it is important to note that that is there. And then we have our base. The base is the acetate ion, which is the conjugate of the weak acid that I put in there. So now instead of having a lot of this and tiny bit ionizing here, or putting in a whole bunch of acetate and a tiny bit ionizing there, we have close to an equal amount, or probably better, significant amounts of both of those things. If I added a strong acid to this solution, so all of those things are floating around, we would think maybe HCl is added to acetic acid and to the acetate ion. We would want to neutralize the addition of that hydrogen ion. Well, acetic acid isn't going to help neutralize the hydrogen ion, so the base portion of the buffer, the acetate, accepts the hydrogen, turning into acetic acid. As it says, it accepts the extra hydrogen. And because this is weak, that doesn't ionize very much, so it may produce a little bit more acetate and a little bit of hydrogen ion, but we do not have that large increase in hydrogen ion that would normally happen if we put HCl into water or into a non-buffer solution. The extra H plus was absorbed, accepted, or neutralized by the base part of my buffer. If I were to put in a strong base, the NaOH would be there, but the acetic acid and acetate would also both still be in solution. The part of the buffer that would be able to neutralize it is the part that reacts with bases. So in this case, it's the acetic acid, part of it. That gives its hydrogen ion, it donates its H plus to that base. So the OH turns into water. We are no longer increasing the concentration of hydroxide ions significantly. We put a little bit, or we create some acetate ion, and that acetate can react with water, slightly changing the pH. But in both of these cases, the weak base turned into its conjugate acid, the weak acid into its conjugate base, neither of which ionizes to significantly change the pH. Putting a lot of OH plus, H plus or OH minus does significantly change the pH. So what's important here is, once again, we have both acid and base in our buffer in significant amounts, and they serve different roles. This one can accept a hydrogen ion, neutralizing, invading strong acid. This one can donate a hydrogen ion, neutralizing that invading strong base.